All right, so we are at the end of our energy and simple harmonic unit. So this is just a quick review of some of the big equations and some of the big concepts that you need to carry with you into our exam that's in a few weeks. First thing that I want to talk about is changes of energy and work. The only way in our class to change the energy of a system is to apply a force to it in the direction that you move it. So if you push on an object, you'll change its speed. You would change its speed, or you would change its vertical position, and you can change its energy. So just a reminder then that work is any change of energy, any change. So your big takeaway there is on our exams, if you see things that are changing speed or changing height or springs that are compressing and extending, and it's asking something about work, what you need to do is you need to stop, figure out the energy at the beginning, figure out the energy at the end, and the difference between those two numbers is the work that's being performed. This FD and this FD cosine theta will show up on some graphs where you see things like F and D, and the area under the curve is the work, but it's not super likely to be how you're finding out how much work is performed. If they're asking how much work is being done, you're probably going to want to look at the change in energy first, because that's probably what they've given you. The big warning to give you guys, and this comes up a lot, and a lot of you guys can get this wrong your first try, but then you'll remember that I said this and kick yourself a little bit. An object that's going in circular motion, its displacement is effectively that direction, its force is that direction. That means an object that's in circular motion isn't changing energy. And we can prove that from the change in energy perspective. If I spun something around my head, it would have the same gravitational potential energy after one circuit, even if it actually isn't flat, even if it's going like this, by the time it does one circuit, it's back to the same gravitational potential energy spot it started at. And if it's going at a constant velocity, or if it's at least at the same speed here that it started at, then its kinetic energy didn't change either. So be really careful on things that are really doing harmonic motion or returning back to the way that they went, because probably no network is being done. Even if you chopped it up into very small pieces, you might be able to say that work's being done. But in the case of something rotating, actually no work is ever done unless it's a vertical circle, potentially, because then gravity could be doing work on the way down and doing negative work on the way back up. But I got a little distracted. Big takeaway, work is a change of energy. Then we have lots of different types, and these are mechanical energies. If we talk about the total mechanical energy, typically what we'll say is that we have a lot of energy transformations, and mechanical energy does a really good job of transferring well. Spring potential energy turns into kinetic pretty cleanly. Kinetic energy turns into gravitational potential energy pretty cleanly. There's not a ton of waste. It's different with stuff like chemical potential. Trying to turn the chemical potential in my body into kinetic energy is actually super inefficient. I create a ton of waste heat. Even if we do it with a car, trying to turn the gasoline, the gravitation, or the chemical potential in a car into motion, again, really, really wasteful. Not a very clean energy transference. But mechanical energy tends to do a pretty good job, not 100%, but pretty good. So that's why we focus on it in this class. So we have three different types of mechanical energy: spring potential, gravitational potential, and then kinetic. And we do have this secret other kinetic, the rotational kinetic, 1/2 I omega squared. But we haven't done it that much with it yet, because we're really going to hit it hard when we get to our rotational unit, where we can understand a little bit more of the variables that are hidden inside of there anyways. So next thing that I want to talk about, and this is probably the biggest idea of the whole unit, is conservation of energy. This is the idea that energy cannot be created or destroyed. All that happens is it either changes form, like between those types of mechanical energy I already talked about, or it moves in and out of the system through work. Most of the problems that you'll do will actually be closed systems where we just have this type of energy turning into that type of energy. And you'll want to set up formulas like the one I have here, where we have the energy at the beginning turns into the energy at the end, plus or minus whatever work's going in or coming out. So make sure that you're thinking about conservation of energy really often, especially on your FRQs. It's almost like a buzzword that you just want to sneak in there as best you can. They do watch. You can't just write the word conservation of energy and automatically get a point, but they almost always give 1 or 2 points for using the conservation of energy, the law of conservation of energy correctly. The last very minor thing, I just put it on here because I had some extra space, is the idea of power. Power is the rate of change of energy use. So for example, it doesn't require very much power for me to just walk, but the minute that I start running, then the change of energy, the chemical potential that's going out of me is much faster over the same unit of time. So just watch those ideas of power, and in particular, watch out for force times velocity. It's not a derivation, or it's not a version of the formula that appears on the formula sheet, but it's one that shows up on questions, and you kind of just assumed that the teacher has talked about it with you enough about it. My grammar got messy there. The idea, trying again, they're hoping that you've learned F times V equals power, and you can kind of derive that on your own, even though it's not explicitly given on the formula sheet. So that's everything that you hopefully need to know just quickly in energy. There's obviously a lot more to it, but these are the main formulas and the main ideas that you want to take with you into the next